All right, let's start with this last tutorial for part 1. So this is question 11. We only give you this single question to test you how to use the modeling, the dynamic model, and the controller design, the Simulink model especially, for some realistic problems. This one gives you a lot of description about a biological system. How do you use this dynamic model to describe certain biological system? In the class, we also learned from the second part that we can use the transfer function, we can use the dynamic model to describe even the student's performance, any of the dynamic system, we can use this kind of model to describe it. So here we would like to bring more real-world examples to you. So in the future, if you want to study certain realistic examples, realistic systems, you'll see you can use this transfer function to describe many processes, and then use this simple Laplace domain function to understand quickly how the system would respond to certain change, to disturbance in the variables. Okay, so here we see the question say the transfer function is given here, the GS, that relates the change in blood pressure Y to a change in the infusion rate U of a drug. So it's a certain drug, sodium hydroperoxide, to have the system response of how the blood pressure within the human body or within a biological system is responding to this input change. So you will see many of the complex problems in your project, in the exams, but you don't have to really worry too much about what really the physical system is. You need to think about better way to simplify it to a model you are able to deal with. It's not exact model, but it's to its best capacity to describe how the dynamic behaviors of the system are like. It's like this example, if you see the GS, it's given as two terms summed together on the numerator. If you separate them, if you look at them as a group, it seems quite complex. But if you consider that as two terms summed together with the denominator to be tau s plus 1, then these two terms can be turned to some of the classic, the standard formats, the transfer function, first order or second order, you're able to solve. Okay, so here it gives you that the two time delays result from the blood circulation that occurs in the body are considered. So theta 1 and theta 2, these two terms on the exponential term are describing the system delay. And here the alpha is a recirculation coefficient. So we have this alpha coefficient before the second term as additional penalizing factor. If you have just a constant, it has constant value. So this is a typical way to describe a realistic process using the model. When you think there's time delay, then you add a time delay term theta. When you think there is certain other coefficient to penalize, instead of just 1, you can consider it's 80%, 50%. Then this alpha here is playing this role. So alpha at 0.4, giving an example, it's like just imagine this coefficient. And in this example, if we see the k before all the terms before the time delay, so if we consider the first order process or second order, all the processes we learned, they have this k as indicated, the steady state gain, right? So we know the meaning of the k describing what's the final delta y over delta u. So this gives the relationship of the steady state gain. And here it is as a unit given here. And also the two time delay terms, theta 1 and theta 2, has the units of time. Moreover, we have the denominator, tau s plus 1. So tau is a time constant. We also consider it describes how fast the system responds to the input change. Like 5 tau, you will reach 99.9%. So this tau term is given here as time constant. So this question asks you to use Simulink to construct the block diagram and simulate the blood pressure response to a unit step change in the input infusion rate. So this unit input, which is from 0 to 1, has a step change. So this is the overall statement. This is a good example of how you can use the knowledge you learn in class to describe certain real-world examples. This one, we ask you to use Simulink to support you, but even without Simulink by hand, you are still able to calculate it by step to get a sense. But Simulink gives you more straightforward platform to see how you can align the software with your understanding of the process. Right, so let's first look at the transfer function. If we don't directly write the GS to the Simulink, it may be quite complex, all the terms grouped together. So one way is we try to decoupleize it to several standard formats, which we can find the corresponding functions in the software, and then use like the blocks to make them together to describe the process. So as we discussed, the GS term given here is for YS over US as a transfer function. Y is the final output, U is the input. As we know, input is given as a unit step change. So we can decouple the transfer function to see what blocks we need for this overall GS. Okay, so if we consider the first term is k to the exponential minus theta 1s, here just 1, so we take this first term out and the denominator is tau s plus 1. Well, the second term, instead of the k as a steady state gain, we have this additional coefficient alpha here. So consider this. If I ask what is the steady state gain for the second term, you will be able to know it's k multiplied by alpha as a new steady state gain for the second term. Because both cases we say it's the standard format of the first order plus time delay model, which you already got very familiar through the project. So this is a typical way we can use this kind of model to describe many process as approximated as first order plus this time delay term. Well, the second term, the time delay equals minus theta. This exponential term is minus theta 1 plus theta 2. So this theta 1 plus theta 2 is a new time delay for the second part. And the time constant is still tau. So this makes a physical meaning as well. If we ask you what the corresponding physical meaning is to this transfer function, you should be able to link it back to how the output reacts to the input. Alright, so since we got this simplified model, we want to substitute all the numbers we know. So we know that k has a value of minus 1 as a steady state gain for the first term. So we put minus 1 here, and alpha is a coefficient, multiply another 0.4. Theta 1 is 30 as a time delay, and the second term has another time delay of 45. So we have this 75. So here is a S here. Solution has a typo here, you should add the S term. Therefore, we have these two transfer functions summing together to form the overall GS. If you consider in the block diagram, which we will commonly use for the control system design, this is no controller, so this is like open loop system. We only consider how the system reacts to the input. Although it's two parts, so if you turn this to a kind of Simulink understandable block diagram, we have the U input, and then this is summation. We can use this parallel form to have U go through G1, and then U goes through G2, where we got output Y1 and Y2, and sum them together to get the final output of Y. So this is what we want to construct. And then the task just becomes how we construct G1, G2, which are both first order plus time delay model. Okay, so since many of you have been familiar with Simulink through the project already, I will first show you the overall model, but also will give you a step-by-step guidance later to see how we can get this to remind you how to use Simulink, because in the second part and project 2, you will use this a lot. So basically, this is the overall model I have. It's not a single unit form. I have a lot of connections to show you. But how to construct this? Let's start from scratch. So now you all know we open our Simulink through the MATLAB interface. So if we have this MATLAB open, we have the blank user interface. And the workspace is somewhere you store all the output, all your numeric output as a data format. So we ask you to save the MAT file through the MATLAB user interface. That is where through the workspace, you can right-click and save your file if there is some data there. Okay, but if not, let's just start from the beginning. We have the Simulink, type Simulink, enter, and start with a blank model. You can try others. Since it's just a simple one, let's just start with a blank model and use the blank interface to start step by step. So here you can directly click the library browser. This will pop up all the components, all the blocks you will use to construct it. One key thing we note here is that Simulink is like a tool to give you all the dynamic description and the calculation. It's like a calculator, or you can do more advanced calculation on it. If you don't want to use Simulink, we can fulfill all the tasks in MATLAB, but this one just gives you another additional nice way to design the block diagram with nice visualization and user guidance. That's how we also ask you to build up the Simulink model in the project. Okay, so when we have that, we always start. We can use the commonly used blocks, or we use continuous so far in this project, as well as sink and the source as output and input. Okay, so let's do this step by step. So for the continuous, you have all those transfer function types, and for the source, you have all different types of input. Let's first get the clock here, so we need to capture the time to know the time step here. As x-axis, we always plot the time-dependent behaviors. And we know another source is a unit step input. So this unit step input can be found also from the source file, or the commonly used block. You found this step. Okay, and we ask you what's the step time. The step time is where you start to respond to the time when the step input u has a value of 0. So we can put the step time to be 0 here, so the input immediately has a output of y of 1. So we have the final value to be 1 as a unit step input. And this is a source. We consider the sink. Sink means like the final one you output your value. The scope or the others is something you can display it. But here we want to get the output to MATLAB user interface and then plot there. So we can just use to workspace. This one plays a role to transfer data between the Simulink and MATLAB. So we have the output to be time, you can transfer it to workspace. You can have another one to output your y. One important thing here is that the default save format is time series. So with time series data, you can see it, but it's difficult to plot it directly. So you change it to array. So you're able to directly see the data and plot it. Similar for y, we can change it to array. So this is important, how you save your data format. Okay, and then the output already, we need to consider either a connection or let's put all the intermediate steps there. The two transfer functions, if you still recall the G1 and G2, they should be added with this format. So let's find what's the transfer function we can add for the G1, G2. So here we go to the continuous again. Because you see, for now, you have learned the control, the basic PID control. You can find all those types of the controller for your further project design. But here we only use a very simple transfer function. So let's examine the form we need. Here we just use this transfer function on top and bottom. We're able to change the coefficient, because for the first one, it's -1 at the k, and 40s plus 1 as the denominator. The time delay term, we will consider it later because it's official. The standard form, you only got a transfer function first. So we can put the k to be -1 here. And denominator is 40 tau s. Tau is it's 40 plus 1. So that's enough. We got the G1 here. You can also use zero pole and other format, or use the state space. It's not covered in this lecture, but we use a lot of the other formats for better demonstrating the system and make analysis. Okay, so you can have the second one to be G2. So this is very straightforward step by step. I believe many of you have done this already. Just want to go through the whole process again, so you can always come back as a tutorial how to use step by step. Again, this second one will recall. This becomes the K, the new statistic gain is minus 0.4, and the tau s plus 1 is the same. It's 41. Right? So now we got the first order transfer function here. Another term missing is the time delay term. So when we have the Laplace exponential term, you know it is the time delay term in the transfer function. When we translate it back to time domain, it's really t minus theta in your time. So it means a delayed term. So in the Simulink model, let's go back to see what is a proper one to describe it. So here I want to bring another key thing. When you use the software, one important thing is how you search the help and Google it to trying to find any useful information. If I haven't used this for a while, I might forget, oh, if I have time delay, what should I do? I forgot which block I should use. But you can always get support from the help file, even from the web resources, or directly Google it online to say how to add a time delay term in Simulink environment. You will find the answer, a lot of answers, and find the helpful one. You can find from the help tutorial to see where we can find the time delay term if you forgot it. But here it's very straightforward. When you see this continuous blocks, you see this one transport delay. If you put your mouse here, you can see what is this transport delay. So this Simulink continuous transport delay is to apply specific delay to the input signal. So the input signal to this block, they will add a time delay. So it's exactly the same role of the exponential term in the Laplace domain. We want to add this time delay. So you can see they give you some more description. So better accuracy is obtained when the delay is larger than the simulation step size. So if your step size is too big, then its delay is just smaller than step size. It won't be shown there. Right? So we have the time delay here. Ask what's the time delay? We remember the first theta 1 is 30 seconds. So we put it here. And second transport delay, it's 45. All right, so when you use the software, don't be afraid of making errors. If you choose another one, just trying to be bold to try all these functions and trying to fulfill your goal. Okay, so this seems what we have for the blocks. But another thing here is we want to do the operation. We have G1 sum with G2. So before I showed you, we can plot it already. We can plot the output from G1, G2, or we can use the marks to add them together. But this marks here is different functions. If you see commonly used block, you can use marks, but you will still plot Y1 and Y2 separately. So for these two to be summed together, we should consider we should use some of the mathematical operation. So if we go to the math operations here, we have all the different kind of operation. You can link the blocks. So here just easy Y1 plus Y2, we can directly use the sum term here. Let's find a proper one to use. It's no single answer, but you can use a lot ways to get your final output. Okay. can use add to get these two terms together. And we have two cents, that's already. So this is what we need for the blocks already. Next one, just to connect all the necessary blocks to have your U. Y, right? So this is directly connect all the terms. You can connect from the end to the south or south to the end. If it didn't work, if the connection does not allow you to directly connect it, you might add another connector like the mux and some other connectors. But in this case, it seems okay. So we connect all the parts together. And what's the next step? Just to run it. Let's try. If we got the format, seems okay. But let's see what the result we can get. So here, because we output all the variables to the MATLAB again, so we got the workspace value from the output is to workspace, right? So we have the time out, we have the Y. But anything wrong here, if I directly run it, if I want to plot my Y, T out. It seems all values are 0. Right. So is this correct? What's the solution I can get? Is it correct? Is this correct? Right, but this is we should say is not correct, because if you see the time output, we have from 0 to 10, because I just use the default value, like 10 seconds here in time step. So it's very commonly if we just use the default value, we may find some abnormal situation. Because in this case, I have my time delay of 30 seconds, 75 seconds. So if I don't run it for enough time, it is correct, but the system is not responding, because within 10 seconds, the system has no output at all. So when you see the results, you might, oh, what's wrong with my model? Did I do something wrong? But it's not wrong. Just you need to run the simulation a little bit longer to see the desired results. For example, here it gives you how long you run the model. So this is just I made this example here, but when you do the example, you do the coding yourself, you may face a lot of these bugs, or sometimes you didn't get desired results. This is the way you go back to examine all parts to see if your parameters are set properly. Is it caused by any wrong setting, or caused by changing any default values? Right, so if we change the to simulation time to 100 and plot it again, we then get the desired response. Right? It is correct to what you get. Your input may be different because you have the different start time. You can start here. I start immediately at time input U is step from 0, and then I got to 30 seconds time delay for the first term, and then the second time delay. If you see some of the dynamics here, it kind of second. Is this correct? Let's compare the result. So here, you see, it is 45 or 75. So I should change it to 75, right? I'm just doing this, like simulate the process. You see the final results looks like this. You need to examine yourself. This seems a time delay, but this is 45. So you should think about if this correct. My time delay for second term seems 75. So that's how I made I didn't change the value properly. I should use 75 instead. Okay. And then we run the model. And then you can see how the second time delay will influence the dynamic response. At the 75 seconds, we got the second time delay term start to react. So that's how, because here when we plot to output to time to the Simulink, it's already a time domain. So from Simulink to MATLAB interface is a time domain response. So we can directly link that to this how the system responds to the input change. If you want to get more understanding, I use this model. I plot both y1, y2 together as output of y, so you can also see them how these two terms y1 and y2 play a role. If you use max, this will give you two plots. So it's basically the first response has time delay, and second one has another time delay. When you add them together, the effects are summed together. Okay, so this is a simple example how I turn the transfer function to MATLAB. When you have more complex models, you are able to design the diagram through a similar process and then get your output y corresponding to the input. Okay, so this is the content for this problem. It gives you a step-by-step instruction for use Simulink, and you might use this. It's a very good tool. You can use it for your system dynamic analysis and controller design for the following of the course. Okay, thank you for being here for the tutorial.